Woo woo. Okay. Hello, recording. All right. So I want to welcome Professor Jay Flynn from CSUN, who came earlier this summer and spoke and was very well received. I've got nothing but positive feedback. So we thought we'd bring him back for more abuse. And let's see if I can get the bio straight. Uh, the thing that I thought was the most fascinating was that there was some competition put out there for universities to apply to NASA to test a lithium battery that did not fail at below freezing temperatures. And they apparently have a policy, they won't fly anything on a mission that has not been sent into space to be tested. So the idea was to give a university a chance to design and build and fly a satellite with this new battery technology on it, and hopefully it would test successfully and they could incorporate this in future missions. So they put this out, and I don't know, 30 or 60 universities applied to do this. And I think I'm murdering the numbers here, but I think they picked 12 to be granted funds to design satellites to do this. And then they picked two to actually build and fly the satellites. Professor Flynn's school, CSUN, State, what is it? Cal State,
California, California State University, Northridge.
Northridge was selected as one of the two, and the other was a small unknown school. I think it was UCLA. And but we won't. They won't go further into the story very far. So anyways, they both got designed and built, and one of them flew successfully. And that, let's just say that's why NASA likes Professor Flynn an awful lot. Um, I don't know what happened to UCLA's, but it's in the dustbin of history somewhere. I got to mute that phone. They never flew theirs, or they did?
No, actually, just a small correction here. The competition was for various missions. Wow. UCLA was not part of the original group, but they had a subsequent competition, and they applied and got a grant to fly a mission in 2019. It was a totally different one. They were measuring some characteristics of the ionosphere, which I think are of interest to us.
Yeah. And did it fly?
It flew and was successful, yes.
Oh, okay. Then I had the wrong story. Well, that's a better story because my wife went to UCLA, so okay. And my sister-in-law teaches there. Okay. So in any case, Professor Flynn is one of those people. We all know people that know about ham radio. And then we all know or know of people who like are authorities. And then there's a very, very few people who absolutely intuitively understand it inside out. I mean, they have the history, they have the science, the math, the real-time operating experience. You know, they have personally used spark gap radios when they were new. Thomas Edison was a relative. You know, Tesla is the car they drive. You know, there's all sorts of connections, most very dubious. But in any case, Professor Flynn is one of those people. He will meet you on the historical, the scientific, the mathematical, and the practical level at ham radio in a way that pretty much is produced in absolutes. I mean, you can take it to the bank. And I'm reduced to very few fingers on one hand of people who I even know of who fall into that category. So that I'm going to make my introduction. Maybe you want to tell a little bit more about yourself, but I'm going to turn it over to you with no more further ado. I give you Professor Jay Flynn.
Well, thank you, Buzz. It's You make me sound, I think, a little bit better than I am. I do one other thing that I was, when the gentleman was sending below 0 degrees, it took me back to my days. I was a radio officer in the Merchant Marine as well. Years ago, I had a broken romance and I ran away, and the Foreign Legion seemed too dangerous, so I joined the Merchant Marine. Anyway, but I used to copy the weather broadcasts, and they would go out at, you know, somewhere between 18 and 25 words a minute, and certain phrases are just, you just hear the sound. I don't hear the dots and dashes, and that's one of them. Below 0 degrees, or degrees, the word degrees, I just hear the sound. Anyway, thank you very much for that introduction. And the last time I gave an outline of basic antenna theory and how antennas are used and so forth. And I want to continue and build on that a little bit. So if it's all right, I'll share my screen. Okay, just doing the proper Zoom protocol. Anyway, everybody see that okay?
Yeah, I see it.
Good. So there we go. So this is, I'm going to do a brief review of what we covered before in antennas. And then I want to talk mainly today about things that affect antenna performance. A lot of times people think, well, I've got the iron in the air and I've got the antenna up. It's a dipole. It's supposed to work. And I don't hear anybody and nobody hears me. And I want to show you a couple of things that might be affecting you and maybe leading to some problems that you might encounter in putting up antennas, and how they work both with the transmitter, and then also how they work with propagation as well, how people will hear you and you will hear them. So I want to go back and review a couple of basic things about antenna theory. And this is, by the way, this is as close I get to mathematics. Last time I put up an equation, I think there was some need for oxygen by some people, and I don't want to do that again. So I'm going to just summarize this thing. Basically, anything that conducts current, or any current, will radiate. And how well it radiates is determined how far something, that current is flowing. So basically, you have some current and it's over some distance, some length L, and you're basically, the product of those two is how well you are getting out. The more current you send over the longer distance, the better you are propagating. And this is really great, and it's one thing that helps us get out in the world. And it's also can be something that hurts us. And it depends on where that current is and what it's doing. And that's sort of what I want to talk about today to some extent. We talked about last time the idea of a dipole. And the dipole antenna is a half wavelength long altogether, made up of 2 quarter wavelength sections, and it's usually fed in the middle. And we also learned last time that the feed impedance has to do with how well the antenna propagates. And like, for example, this antenna has about 73 ohms is the feed impedance. If you took a, if you will, an RF ohm meter, you can't do it with a regular ohm meter. You'd have to do it with a special ohm meter that you would look here and you would see 73 ohms. And that's because if I put certain current into there, if I put a certain amount of current into there, this is effectively the way that the power is going into the antenna, never to return. It looks like a resistor. You put current into a resistor, it heats up, that current just disappears. That power disappears as heat. In the case of an antenna, it goes in there. It doesn't warm up the antenna, hopefully, but most of it goes off into space. And then we also looked at the vertical antenna. If I get too low, somebody holler, which is over a ground. So this is over a flat ground. And this has 50 ohms. And part of the reason why it has a lower, if you put the same current in both of these antennas, the same RF current, this one would radiate a little better than this one. And the reason is half the antenna is missing. You don't have the full length. This is only a quarter wavelength. And so we see that there's a slightly different impedance there. So if you put the same current into both antennas, this one would radiate more power because of the relationship between current and resistance. It's I squared R is equal to the power out. Okay, so the same current going into the this antenna would be get out more. So again, it is basically this equation, this simple equation. Basically, the more distance you have with the same amount of current or more current, you will get out better. But the thing is, many of us are constrained, and we have short antennas which have various ways of doing that. One of which is you have an antenna and it has a coil in the middle of it, and it still looks like 50 ohms. Let's say it's a vertical on your car or something like that. You still have the 50 ohms, but a lot more power is being eaten up in the antenna and less is being propagated out. It looks like 50 ohms, but it's because the presence of this coil is helping things work. It allows the antenna to be shorter. So this is less than a quarter wavelength, and it looks like 50 ohms. So it talks to our transmitter and plays nice with our transmitter, but it has its reduced length. We have the same current going up into the antenna, but the antenna, this inductor sort of fools the system into thinking that, yes, we have 50 ohms going out. So that means I'm radiating the same as this guy, but you're not. So shortening an antenna costs you something. And so if you're already in a situation where you're a beginner, and you don't have a lot of real estate to put up an antenna, you're maybe at a disadvantage already by using a short antenna or some kind of other antenna that is limited in space. And you're wondering still, okay, I see my power is going out, everything is happy, my transmitter likes my antenna, there's no bad reflections, and I'm still not doing exactly what I want to do, because you may have the short antenna already, but there's some other things that might be affecting how your antenna is working. So I want to go into that and talk to you a little bit about the whole system. No antenna operates all by itself. Every antenna is part of the world. It's the link between your transmitter and the world. Everything. So you're putting power into it, and it's trying to radiate that power into space that goes around the world, hopefully, and talks to your friends. But there are things in the way that are near the antenna and along the way to the antenna that can cause some issues, and you should be at least aware of them. Maybe some you have to live with. Okay, you may not have 3 acres out in the middle of nowhere where you can put up as big an antenna as you want, a 300-foot tower and all that. You may be in an apartment, you may be in a small urban lot or a small residential lot, and you have limited space and you have what's around you. You can't sit there and go to your neighbor and say, hey, you know, that big tree you've got over there, or that big flagpole or something, I'd wish you'd take that down because it's getting in the way of my antennas. So, and there's also geography and things like that. So we're going to talk about that today. That's my main subject today. And we'll start with breaking it down. We'll go from the transmitter. So most of us, your transmitter is, maybe a constraint of cash, it may be constrained by space, whatever. There's also licensing. So you have a certain amount of power to work with. Okay. So we're concerned about getting that power safely to the antenna where it can do its work and the most power possible. And so there are a couple of things that can happen. So I want to talk briefly about a couple of different types of transmission lines. So we all are familiar with twin lead. Some people use this. So basically that's two conductors, okay, going off from our transmitter off to our antenna. And this is not necessarily to scale, but basically you've got two wires. And if we looked at that basically end on, let's watch what's happening with those wires and how where we put those wires could be affecting how they work. Now, this typically, depending on the spacing of the wires and everything like that, it's typically available in 300 ohm wire. And they used to do some things with 600 ohm feeds. But let's look at somebody's using this 300 ohm wire. First of all, you've got a problem in 300 ohms is not 50 ohms. So you've got some issues there. But maybe you can, there's ways that you're trying to match this. There's certain types of antennas that use this. But what can be going wrong with using this? So basically, you might ask the question and say, well, wait a minute, if I've got current flowing out this wire and it's coming back this way, you've got current in a wire, you just told us it'll radiate. And that's true, it does. However, let's watch what happens. If I have a current going into the paper here, which I'll indicate by the X. So the current's going in, and this is where the current's coming back. You'll get, let's look at some of the fields that are going on. We're going to take a look at those. So if it's going in there, we can use, there's a rule about it, but basically the current will cause a magnetic field around the wire that will go this way, okay? The other field, because the wire is coming out, will go in the opposite direction and go around this way. And I'm only going to concentrate on the magnetic field for now. But anyway, we've got these two fields, and notice in the middle, they're both going this way. But let's look what's happening farther away. This wire will be producing a field going this way, and this wire will be producing a field going in the opposite direction. It cancels. They cancel. Outside of the wire, well, pretty much, shall we say, far removed from these two wires, the fields are canceling. So there's no radiation. The radiation, it's what they call self-shielding, in that the two fields cancel each other out. And so out here, we would see basically zero power at those two distances. However, notice what's happening as we get close to this. This field here is going around here, but because it's closer to the wire, this one is, and it's slightly farther from the other wire, they will try to cancel, but there will be some field here and some field here. It falls off rapidly to zero, but there's an area around here where there is a field. There are fields here. You've got to keep anything away from that area. So for example, if you took this twin lead and laid it over a roof gutter going up to your antenna, the gutter is close enough, it's a piece of metal, it's close enough, it will interfere with this. The fields will not be able to go properly around. They will hit this metal and they will be distorted, and the twin lead will not work very well. And so you can get into issues by using twin lead. If you're using an antenna that involves that, you keep it away from other materials. And I would say a good foot, or approximately, what is that, basically 30 centimeters, would be a good distance to keep twin lead away from other metallic objects. so that it doesn't interfere with that. By the way, I can take questions at any time, although there will be definitely a question and answer period at the end. Now, coax is more popularly used, but it also has a couple of things that have to be watched out for. So coax is, if we looked at a cross section of it, you have an outer shield and an inner conductor. So I'm going to make this shield thick so I can do stuff with it. So we have that, and inside here is either air or a foam or a plastic dielectric. It's a piece of plastic. It's an insulator between these two conductors. And again, we do have, let's say, a current coming toward us, and the current going away from us is on the outer conductor. Okay, so we've got that going. Now, it turns out with coax, there's a couple of things that happen. There's also an electric field in here that is between these two. So you can think of electric field as something that talked about in voltage. There's a voltage difference between this inner conductor and the outer conductor. There's also a magnetic field, again, just like before. And the magnetic field is affected by the distance, the amount of current that's going through this inner conductor. And then the outer conductor will also have a magnetic field associated with it going in the opposite direction. Unlike twin lead, the electric field can't escape because this is a shield. This is an enclosure. The electric field cannot go through the conductor. It's stuck in here. The magnetic field, it turns out, because of the fact that this is a circle and this is a bigger circle, it turns out that the fields right at the outside surface, right at the surface of this outer conductor, they totally cancel out. There is absolutely zero, for all intents and purposes, outside of this, even very close to it. You'd be hard pressed. But there's a few things we have to watch out for. So coax is very good. It's, first of all, it's 50 ohms. Got to watch it with dipoles, but you can use this on a vertical or an inverted V, which has a 50 ohm feed. And this is the most popular one because you don't have to worry about where you lay it. You can take it off your transmitter, lay it on the floor, it goes out the window, up the side of the house, up the side of the tower if you've got one, or the metal pole in your backyard. It doesn't care. Nothing, it doesn't know anything that's going on outside of here at all. But there's a place where things can get out of hand and we have to be careful about it. So we've got this electric field in here, which is causing this current to flow in both the inner and the outer conductors. And basically, because of certain rules of physics, that current is flowing primarily, if we blew up that outer conductor, if we blew that up now, make this bigger, okay, that current is primarily here. It's on the inside. It flows mostly on the inside, and there's practically no current flowing on the outside. Okay, I'm getting off the screen, sorry. And you've got practically no current out here. And that's what you want to keep. You don't want current coming on the outside, because then this piece of coax is going to, what do you think is going to happen? It's going to start radiating. It's going to become part of your antenna system, and it's going to be a part that may not cooperate really well with what you want to do. So we want to keep these currents zero. But the question is, how do they get outside? Well, I'll show you one way. A lot of times people will take a piece of coax cable and they will use it to feed a dipole antenna. So you've got, here's your dipole, and they have the coax, and it has the outer conductor, and it goes right to there. we have our little bit of foam insulation, and then we have our outer shield, which is usually a copper braid of some sort. And then there's insulation over that, but this is the outer braid. Okay. And so the inner conductor goes to one side of this and the outer goes here. Okay. So that looks pretty good. And if this was a good match and everything, all the power would go out to the antenna. However, there's no such thing as a perfect match. And also we have something else. This is very near the antenna. This is right in the middle of it. Okay. And so there's all kinds of fields that will be associated with this. There's a big magnetic field right here near the in the center, and there's huge electric fields at the tips, all of which are trying to operate, and they have lines of energy that are going back and forth, and look where they're hitting, right there. This has become part of your antenna system, and what it can cause is currents coming back this way on the outside of the of the cable. And what this means is this length here is now part of your antenna system, and you may end up with difficulties because of that. It's because you have certain currents that are going into the antenna, but some are also coming back out, and they've got to go someplace. One place they can go is right back into your shack, your radio room. And you can get some very strange effects, like every time you touch the transmitter, it tingles or just burns when you're transmitting. And that's a condition. And then also, even if you ground this, if you grounded the cable and said, okay, I want to be safe about this, I'm going to ground my cable, this has now become a radiator. This is now radiating in a way, and it's using up power. That radiation only comes from one place. It comes from that transmitter, and it may not be going the way you want, and it may be affecting the other things, as we're going to see. Everything, remember I said, anything that conducts current and has got current on it radiates itself, okay? Well, that radiation can go back into the antenna. It can actually bounce, if you will, comes out, hits the cable, goes right back into the antenna, and it can cause currents to flow itself. And these currents may not be helping you. So what can we do about this? Well, the simplest thing to do is to use what's called a balun, a one-to-one. And what that does is it's a balun, stands for balanced to unbalanced. So what do I mean by that? So we have a balun, okay, balun, balanced to unbalanced, okay? What does this do? Why do we need something balanced? Well, because you want this current going out this way to be the same as the current coming in here. All right. If we've got a certain amount of current that's going back down the cable for whatever reason on the outside, this current will not be equal to the other one. So your antenna is not doing the way it's not operating the way it should. And so typically what a balun is basically it's a transformer essentially. And it's two windings that are sharing a single core between them. These, you can buy these. They're available, and some dipoles come with this. You can buy dipoles, commercial dipoles, and they'll have a balun with it, or you can buy one separately. But basically, what this does is it ensures that if the current that's going up this side is the same as the one coming up this side, and then you can attach your coax on the other side of this. So your coax would be attached down here with its outer jacket, okay, just like before. But what this ensures is that the currents are the same, because this transformer makes that happen. It also does one other thing. oops, I'm off the screen, way off the screen, and nobody's screaming. Anyway, the one thing that this transformer can do is also it blocks currents that aren't balanced. In other words, if I tried to force a certain amount of current down here by some magic, if I just said, hey, I want that current to flow here, trying to make this unbalanced. In other words, there was more current in this leg than there was over here. So let's say we had this had a 1 amp going and this was 1.5. The transformer would say, I'm not letting that happen. I am going to make sure that these are equal and these are equal. All these currents are going to be equal, and it will block any kind of current that is trying to get back down the outside of the shield. So this is a very important thing. Some people think, well, do I really need it? Yeah, in a pinch, yeah, throw something up if you really want to get on the air. But I would recommend using something like this because it prevents these currents from coming back down, and it forces things to be the same. And it keeps currents from coming down, and it keeps your coax from really becoming part of your antenna system. All the radiation occurs where you want it, up here on your dipole, not down in your basement as it's going out the window or out inside your apartment, where it's not helping anything. So, by the way, there's one thing that I mentioned, and I don't know if I went into it in great detail last time. There's something about antennas that's called reciprocity. An antenna that is a good transmitter is also a good receiver. And if you've got currents that can flow up and down this outer cable, and then they can come from the antenna, they can also do the reverse. In other words, you've got a signal that your coax, let's say your coax is going past a noisy piece of electronics, or it's tied to some piece of, like your computer generates a lot of radio noise. So there are certain types of switching power supplies that just are horrible. What it does is it keeps that noise from getting into your antenna system as well. It works in reverse. So this thing doesn't radiate, the coax doesn't radiate. And so it's not going to act like an antenna, which also means it will not pick up bad signals as it goes by things. So it's a good addition to have in any kind of system, is a balun. Okay. So I'm going to move on now, watching my time. I want to talk about something else that's often in your antenna system, and often because it's something that we really can't do anything about, we often say, well, I'll just live with it. Okay. So, and that is the ground. We all live on planet Earth, and some of us live up in an apartment building, but even there, okay, you're still dealing with that apartment building is acting like a ground, and it can, but those of us who are on, city lots or even residential lots, we have ground. And there's an old saying, ground is ground the world around. Well, no, it depends on where you live. So for example, I live in Los Angeles. The ground here is very dry as a rule, and it's extremely dry right now. It is not a very good ground. Okay. Those of you who live near the ocean, it's a better ground. If you were actually on the ocean, it would be a really good ground. And those of you who are like in the Midwest of the United States or in Central Europe, you're probably talking about a fair ground. It's a pretty good ground. But the thing to remember is, in most cases, even by me here in Los Angeles, it conducts. It can conduct. Maybe not a lot, but it does conduct. So let's look at a couple of things that would happen here. So let's say we have our dipole up in the air, and we've fed it with our balun, and we're all happy, and it starts to radiate. So we're sending out our first signals, and they start to radiate. And we have a big magnetic field in the middle, and let's just look at the electric field. So the electric field goes basically from end to end, and what's going to happen here, it's going to hit the ground here. And this depends on how high your antenna is above the ground. Okay, so if the antenna is very high, this field here may not be that strong, because there's a couple of things about antennas, and I won't get into the math. There is the field, there's actually 3 electric fields, but let's just concentrate on 2 of them. There is the field that comes off the antenna that radiates, that carries your signal around the world. Okay. And then there's another field which it dies off very quickly. In other words, because of the mathematics, it fades away within probably several wavelengths of your antenna. If you're more than a few wavelengths away from your antenna, that field is gone, and all you're left with is the radiating field. It's going off and taking your words around the world. But close to your antenna, there's this other field, which is commonly called an induction field, because it can induce currents. So now I have this current up here, and I have another current on the ground, okay, because of the same field. It's being radiated. That current will cause what? I've got a current over a length of ground. It's going to radiate, and it's going to radiate a signal back up to your antenna. And the closer you are to the ground, the more this will occur. And what will happen is that radiation goes right back into your antenna. Remember, an antenna doesn't care where a field is coming from and how it's made or whatever. It says, that's an RF field, I've got to receive it. And that may cause, if you're not careful, currents to try to flow in the opposite direction. So I'm going to call this reflected current. And what do you think that's going to do? It's going to fight this. One, it's going to reduce your propagation because it reduces the overall current in the antenna. And that current's got to go someplace. It's going to go back into your transmitter. And it's going to show up as high SWR. In other words, the match between your antenna and your transmitter, even though you were very careful here, and this, by the way, has nothing to do with the balun. This is coming in the antenna itself. And it can be a big signal that comes back in and gets into your radio, and your radio says, wait a minute, I don't like this anymore. I'm getting power back. It's getting too much power. I'm heating up. I've got to stop. Okay. And you can get this kind of effect. And so, for example, you have an antenna that works really well on 15 meters. You've got it up in the air, and then you say, well, gee whiz, I want to get on 80. So I just lengthen the wires out and I make a bigger antenna. And now it's still at, let's say it's 10 meters in the air, or even 15 meters in the air. But now 80 meters is 80 meters, and it's a heck of a lot closer in radio terms to the ground, and it will have a bigger reflection. So it'll work on 15, but it won't work on 80. Okay. So you may say, well, all right, how do we get around that? There really isn't a way with this current setup, but this does give you an idea. Typically you want this to be like a good half wavelength. A full wavelength is better. Okay. It'll cut down on these reflections. And there are one other way. So typically what people say, well, if I can't beat the ground, I'll live with it. I'll use it. Okay. So what you can do, you decide, okay, I'm going to put up a vertical, because the vertical uses the ground, doesn't it? Okay. And I'm going to feed this, and this will feed with 50 ohms. And this is a quarter wavelength high. Okay. Which I can do on 80 meters. It's a pole. It'd be basically, I got to do my math, 20 quarter wavelength is 20 meters. So a tall tower, but I don't have to worry about reflections. And so I'm using the ground, aren't I? Yes and no. There's something you also have to do here to help you. Remember, I said the ground in certain parts of the world is not very conductive. It depends on where you live and everything. So what you can end up doing is you have your field from this antenna, which is trying to go off. Okay. And it is actually causing currents to flow in the ground. But this is got resistance. Okay. You have a resistor that's now in your antenna system. It's not a very good thing to have because that means this will basically give off heat. And if you've got enough power, the worms will come out of the ground. Okay. So you can lose heat here, and which means that you're not radiating. You're basically warming up the ground around your antenna. So if I look down at my antenna, now this is my vertical, I'm looking straight down at it. I'm looking down from above. And so I'm looking down this way, down from above. I would have my antenna pole there, and I would want to make sure that this ground is a good ground. And so I would string along the ground or just below it what are called radials. And you would get, it eats up a lot of wire, but it makes everything work really well. Typically, they say, some people say 120 radials, other people say you can get away with 16, some people say 3. Basically, the more the better. Because what this does is it forms a return path for that field. Okay. This field now, instead of flowing through the dirt or the sand or whatever you've got underneath your antenna, there's a circuit, this wire forms an easy path for it to get back there, and we get rid of the heating. We are now using the ground effectively to get our signal out, and our antenna is working better. Okay. So we talked about height and about the height above ground for, let's say, dipoles, and let's talk a little bit about height in general, because it has to do with something that we, maybe as DXers, if you're looking at long distance communications, you want to have work for you. Okay. And basically, it has to do with something called the takeoff angle. So let's say we have our beam or our dipole is up here, stretched out, and we have it a certain height above the ground. All right. And let's say we've got it high enough that we don't have the reflections. What'll happen is there will be a certain amount of the energy that will come down, hit the ground. That causes currents to flow. The ground re-radiates that back off. And what'll happen is you get a direct path as well. And the two signals, by the way, am I off on the right? Trying to get that back in. The two signals will combine, and they will cause basically, if you looked at this a little bit as a smaller scale, you've got your little antenna here, and you've got the ground that you're on. It will cause your radiation, your maximum radiation will go off more above the horizon, okay? And so it bends, it causes a bending of your radio your main transmission. So this would be if I looked at my antenna and these were different directions from the antenna, and this represents the intensity of my radio waves or my radio signal coming off of there, we would see that most of it is aimed off this way. And typically, if you want long distance communication, you want it as fairly close to the horizon. If you bring this down even lower, so if we had another case here where the antenna was very close to the ground, you would end up with something where the most of your radiation would be going up at a very high angle. So again, this is another characteristic, another time where height makes a difference, because again, you are inducing currents on the ground, yeah, and they're also in your antenna. Those are both radiating now, and there's a signal being reflected off, and it's bending your radio waves up into the sky. So again, higher is better. Okay, it helps you with your SWR. because you don't get the signal being reflected back into your antenna like we saw before. You don't get this, but you also don't get, you get a lower reflection angle, okay? There are, by the way, people that use this actually to an advantage there. It's called near vertical ionospheric. What is, I gotta do NVIS, what is that? Oh, shoot, I just lost the acronym. But anyway, basically, you're almost sending a signal straight up so it comes straight back down to people nearby. It's basically how you're trying to do short skip. But you want this to, if you want to do it, then you should know what you're doing. I don't want you to have, the idea here is for you to understand what might be affecting what you want to do. So sometimes this might be good, but typically if you want to talk long distances or get out very well, you want that antenna up as high as possible. So I just want to cover one more thing in today's talk, and that is it has to do with other things that might be nearby. We talked about the ground. Remember, whenever you have a field, whenever you have your field, you have and then you have the ground here being a conductor, okay? You can have it so that this is conducting, it creates a current. You have an electric field, a conductor, you get a current. The current can also re-radiate, okay? So, and as we see here in the case here, this can affect your propagation. Oh, and by the way, remember reciprocity. What works well in one direction works the same in the other. So if you're trying to listen to some signal that's coming from far away, this antenna will not hear it because it's so low. It will not hear it as well as one that's higher up, because your antenna, it propagates well in this direction. It hears well in the same direction, okay? So let's see some other things that can get in the way of things. Typically, we live in a world that is made of stuff, okay? Let's start with things like trees, vegetation. At our frequencies, typically trees and vegetations have very, very minor effects. They have water in them, yes, but it's not, shall we say, it's not the best conductor. So typically you don't get a whole lot of trouble with trees. However, light poles, other buildings, nearby, let's say you have changes in terrain. I happen to know somebody who lives on the side of a mountain and has to deal with this. Yeah, I saw you, Buzz. This is a big problem, because if you have nearby objects, so let's just draw, here's your lovely ham station. You've got your house here, and you've got your antenna up in the air, and you've got, let's say nearby, we have a pole with power lines. Never too close. Stay away from power lines, folks. Do not put up antennas near power lines. One is, if it falls down or the power lines come down, you are going to in a world of hurt. You can get killed. If you're up there working on the antenna, stay away from power lines. I can't say that enough. Anyway, so you've got this pole. If this is a metal pole, you're really going to have to deal with it. If you've got even your house being nearby, it can be a problem. Sometimes telephone poles, if you look carefully, they will have a wire running on the outside. Sometimes, I don't know, it varies around the world. They will have a wire for lightning or a safety ground. And that wire is what? We're going to have a big field coming out from this. This will reflect back to us. If this is close by, it may change our SWR. If it's, and the power lines themselves, the wires themselves will interfere. But they will also change our pattern. In other words, which direction are we listening and we're trying to hear? Buildings, big buildings, of course, will really reflect, okay? And if you have a mountain or a hill, it may block the signal entirely. So you have a number of issues here, and all of these involve basically your antenna putting out a signal. A conductor nearby is got a current flowing through it, and it's radiating back to you. The same thing happens on a building. Your signal is going out, it hits the building, and it radiates back. Okay. If these are far away from you, typically they may not affect you. Like, you may notice the SWR is a little off. It's not perfect, it rarely is, but they will affect where you can hear. Okay, power lines can really block the signals coming from certain directions, because that signal will, because of reciprocity, basically, your signal will be bent by the presence of these other conductors. Just like the ground caused your propagation to bend, this will also cause it to bend. This hill will obviously cause it to bend. It will tend to block it. Distant hills are not such a big deal. So if you're like, several miles from a hill, unless it's a huge mountain, it probably won't hurt you. But if you're hard up against it, yeah, you're not going to hear very well from behind that hill. And it's important that you realize that this may be something you have to live with, unless you find a friend that will let you use his or her ham station, and they're on the hilltop or something like that, or you get an antenna all the way up there. Anyway, I wanted to wrap up here so we didn't go too long and had time for questions. But just remember that, oh, and by the way, fences do it. Okay, metal fences, any kind of other metal structure, street lamps, all those sorts of things. And you can get especially power lines. Power lines can really distort, because typically in the United States, what is the height for power lines? I think it's 30 feet. And that's where we like to put our antennas, where we want to be up at 30 feet. A lot of times you're limited by building codes. The government says you can only put up towers so high, so it's difficult to get a tower up above the power lines. So you may have to live with that, but just understand that that is going to affect you. So with that, I think I'm going to wrap it up. But just remember, just as in summary, be aware of how your signal is getting to the antenna, and make sure that it gets there in one piece, and that your antenna cable is not part of the transmitting system or the radiating system, unless you absolutely have to. Like if you have a wire antenna and you're running it from a tuner on the ground, okay, your wire is going to radiate, and that's maybe a good thing. But if you're running coax up to a dipole, use that balloon. It will keep noise out of your antenna. It will help you radiate properly and keep RF from getting back in your radio room. The other thing is, when you're dealing with your antenna, make sure you understand that if you have it close to the ground, you're going to get reflections from the ground. They can affect your SWR, because that energy going down to the ground is bouncing right back up and going back into your transmitter. Your antenna is receiving it, it goes back in, and your radio may not like that. If you're going to use a vertical antenna, make sure that you look into using radials. If you're trying to use low frequency, you want to do some low frequency work, use radials on the ground, because you don't want to just be heating up your ground. And then keep your antenna away from other tall objects, metal objects, as much as possible. If they're close by, you'll get that re-radiation effect, and the signals will come back in there. But it will also, even if they're, let's say within 3 or 4 wavelengths, they will affect even how you hear. So this will affect big things. Otherwise, like I said, a hill, just understand that it's there, and you're not going to hear it too well on the other side of that. So I'll open it up for questions now. Or thunderous applause, one of the two.
Go ahead, Joe.
Yeah, thank you, Buzz, and thank you, Jay. Boy, Professor. Pardon me. I'd love
Jay
to
is
sign.
just fine. I don't know why
Okay.
he introduces me as professor, but
Well,
anyway.
he probably owes you money. I just want to thank you. First of all, I would sign up for one of your courses or whatever it is you do. You make this all so clear. I really appreciate it. I have two questions. I operate most of the time either portable or mobile. And so I use a vertical antenna for the most part. I would like you to just quickly address the issue of the length of radials, just some
Oh,
theory on that, because you did mention that. And the other question is somewhat related, and that is the length of the coax going from my transceiver to the balun on my vertical. Which, and I'll just say, I have to vary that sometimes. I have a 50-foot chunk because sometimes I'm running at only 20 feet or so, and sometimes I have to run it out all the way to 50. And rather than chopping it down, I just
yeah,
have kept it at 50 and keep it kind of coiled up.
yeah.
So radials and coax.
Okay, so when you say portable, you're talking about you're out in your car, but your antenna is not mounted on the car.
Well, well, sometimes I use a ham stick, great
Yeah,
compromise,
yeah,
mounted on the car, and I run the coax inside.
right.
And sometimes I have a Wolf River coil that I use for POTA on a
Yeah,
tripod.
yeah.
Uh,
Yeah, and so here's the deal on, operating in a car, you're at a disadvantage because I don't know how big your car is, but it's certainly smaller than a quarter wavelength, but it is large. I mean, it's not a piece of wire, it's obviously a hunk of metal that has a large area. And so that can be a very effective ground. The problem you have is largely due to the fact that you're usually using a smaller antenna with a loading coil on it. Is that right? That will be your biggest drawback there. Um, Now, as far as your portable operation with radials, so your tripod mount, you say you're using the vertical with a balun at the base?
I may have confused it a little bit here. I sometimes use about a 32-foot vertical pole with a wire on it, and that goes to a
Yeah,
4-1 balun.
a 4-to-1.
Yeah.
Okay. So a 4-to-1 balance, so you're using it for impedance matching, and then I take it you're using you have some kind of tuner?
Yes, that's right.
Yeah. So what you've got there is you said 32 feet?
Yeah, approximately. That's
Yeah,
right.
give or take. Okay. So what you have here is you have a non-resonant system. So part of the reason about varying the length of you're coiling up the coax and things like that is you are going to get RF flying back here, and the balun here will help a little, but I think yeah, I think your bigger problem is the reflections inside your cable. And I take it the problem is your tuner just can't reach it to tune it in.
No, it'll tune it in, but of course I suffer with power loss.
Yes, and that's simply because you're eating up power in the cable and also the balun and other things. And you said what are you using for radials here?
Well, I use the chassis of our motorhome,
Oh,
which is a big chunky piece of several big I-beam kind of things that go
yeah,
underneath it. And I usually put out at least one radial, sometimes more. And the reason not more is that we're oftentimes confined to campground
right,
spaces where we don't
right.
have, yeah.
So you've got this. How far away is the mobile home from the antenna?
The antenna's attached right at the back of the mobile home.
Oh, so is it down low?
It goes all the way down to the ground, yes, and then up for a total
But
of, as I
so it's
said,
right
about
up against hard against the mobile home?
not hard,
But
but a matter of inches. Yeah.
all right, well, that's hard against it. So you've got part of your problem is you're going to get massive currents induced here because your antenna here, I'll redraw this more like you've described it. So you've got this thing where you're feeding this and this is going to the mobile home. So your ground is attached to the mobile home, right?
Yes, that's right.
Okay. And then you're feeding this with your 4-to-1 balun and everything like that. And this is a matter of, you said inches. Okay. How tall is your motorhome?
About 13 feet.
So you're up here. Let's say this is almost at the ground. So let's say this is 10 feet up. So you got 10 feet of your antenna is basically a transmission line over a ground. So basically this part will not radiate very well. Only this upper part here, which clears. So this is 10 feet. This would be another 22 feet according to your what you've described. So basically this is more or less a transmission line, because if you've got a wire operating over a ground surface, you are basically creating a basically half what they call an image twin lead. In other words, you've got a ground in the middle and you've got a wire running over it. Okay, so here's your twin. Remember, I talked about the twin lead problem. What you have is you don't have this part, you have a ground in the middle. Okay, and you're going to get, the field will be between there and the ground, and magnetic field will be constrained. It won't this part will not radiate very well. Especially since your mobile home is already part of your ground system. So this part is not. It would be better if this was up higher.
Yeah.
That would work, or even on top of your motor home, if you could do that. I take it that might be a mechanical issue or things like that. But the other thing is, when you're operating this at various frequencies, you're going to get reflections. This will be partially inductive or capacitive, depending on what frequency you're on. The length of your cable is going to transform that into other impedances. Your cable is, by the way, how long is this piece of coax? You said 50 feet?
Yes, that's correct. Yeah.
Yeah. So that no matter how it's coiled or whatever, it's going to cause, it's going to transform the impedance seen here to something else seen at your tuner. There might be a certain amount of loss depending on the mismatch. Here you may get losses in the balun and in the cable, but it usually has to be pretty awful in the cable. I mean, it has to be above basically 3-to-1. I'm not talking when you use the tuner. I'm talking about if you sent the cable without the tuner into right into your transmitter, you would see basically like a 3-to-1. Well, that 3-to-1 doesn't go away. It just, the tuner protects the transmitter from it. So you're losing, you're eating up, you're sort of fighting yourself a few places here too.
I'll say thank you. That's very helpful.
Yeah. And the radial, I don't think the radial is going to help you much unless you move the antenna away from your motorhome. But this is a very common setup. I've seen this. I mean, they used to use this in military vehicles.
Okay.
And it was done for mechanical reasons.
Thank you.
Sure. All right. I see hands up. Oh, goody. So, Alex, you're at the top.
Jay, excuse me, 2 questions. If you're using a 1-to-1 balun in the line from the antenna, and in this case, presumably it'd be after the 4-to-1, is there any gap of distance between the antenna or the balun and the 1-to-1?
So you're suggesting this?
Yeah.
So this is 4-to-1, actually 1-to-4. And this is 1-to-1. This is not going to buy you anything. It's actually going to insert more loss.
Then if there is not a 4-to-1 or 1-to-4 balun, if you're just coming down from the antenna near the midpoint.
You know, a dipole or a vertical like this?
Either one.
Okay.
Is there a... Is it closer the better, basically?
Yes, closer the better. It should be, actually, typically, they have, I've seen them, they basically have a box like this with big lug nuts on the side.
At the midpoint.
And it's right at the midpoint of the dipole, and you have the balun is inside here, and there's a coax connector on the bottom.
And the second part of that question is, a one-to-one toroid balun or a dirty balun coil?
Okay, so a dirty balun is, yeah, so what he's talking about is basically you take a bunch of coax and you make a big coil with it. And that acts more like a choke. But the problem is it works better at high frequencies than low frequencies. So you can, yeah, 10 meters, 15 meters. Yeah. I used to do this with a 15-meter dipole. They recommended, what was it, 15 turns or 10 turns or something. What this acts like is a big inductor. And it keeps the currents, it presents an impedance so that the currents cannot flow down. They can't get going this way. And it does act as a balun to a certain extent. The toroid balun allows you to extend the low frequency down to, like, 80 meters or 40, whatever. Some of these, by the way, they use just basically a slug in here. It's what they call a bifiliar wound. It's basically two wires wound around basically a slug. And they act like chokes. And it has the balun effect as well. But this is okay in a pinch. But like I said, don't expect it to work down at 40 or 80.
Thank you.
Yeah. They used to call it a coffee can balun because you wound it on a coffee can. Anyway, all right. So let's see. I don't know. I guess this is in order. So I hope it's not, no, it's not alphabetical. So Kuba.
Two questions.
Yes.
You mentioned metal objects that are close to my antenna. What is dangerously close? Let's say in lambda, because it depends. Yeah.
Yes.
Metal fence, metal roof.
Yeah. So depends on the size. But basically, the zone that you want to keep things out of the induction zone. The induction zone is where you've got this extra field that is going to help generate these extra currents. And by the way, this induction zone that's how, by the way, they use that on a Yagi. They use that on purpose. And that's why it's such a brilliant solution. However, it's typically recommended that if you go out more than, let's say, if you're out 3 wavelengths or better, you basically reduce that field by how much? That's about 10 times, almost 10 times. If you're at 3 wavelengths, you reduce that field 10 times. And so it will, severely degrade that. So basically, it depends on your frequency. If you're at 10 meters, you're talking about something within 30, of course, and so forth. And that depends again also on how big it is. If it's like a quarter wavelength, it's going to really re-radiate back to you.
And second question, you said about reciprocity.
Yes.
And it's a known concept.
Right.
But somehow I cannot add it to separate receive antenna like beverages.
That's correct. You can't. No. Because actually, a beverage antenna uses the fact that the ground is you usually do it over a poor ground because it's a kind of an interesting theory. Basically, for those of you who may not know, a beverage antenna is mounted over a ground like this, and it may have a balun on the other end, but basically your receiver is down here. This may be terminated depending on what you're doing. But basically what's happening is you've got the radio wave coming onto here, but because of ground reflections, the wavefront gets bent, and think of it like dragging a curtain along the ground. And you get this effect where it starts this would be the E field, and there's a sizable amount of this that induces a current here, and this E field is like pushing it along. And so what happens is you get basically this buildup of signal that's fairly large by the time you get to the end here. So you're using this as it's like what's called a traveling wave, because you're pushing that current along and you got that E field going with it. And there's very effective. But yes, I wouldn't recommend, you can do transmissions with this. In fact, they used to do this at very low frequencies. However, this would be on the order, you could have this is on the order of maybe 4 or 5 meters. Okay, if you want to do it in the opposite direction, you want that thing way up in the air, because now the ground is your enemy. It's just going to eat up power. Okay. All right. Ken.
Yeah, I'm going to have to change out, I'm moving my antenna. I'm going to have to change out the cables on it. What would you recommend for cables like RG8U and R213? Which one would you recommend for HF? And then the same question for VHF, UHF.
Okay, so offhand, I can't give you the VHF, UHF, but basically at HF up to 30, you know what your biggest thing to worry about is the insulation on it. Because oftentimes you want cable that has RG8 will work, 213 would work, but what happens is when the outside insulator is exposed to ultraviolet, it can cause micro cracks in there. And I see you're in Illinois, and I know it rains in Illinois because that's where I'm from, and it snows and all that nasty stuff, and water will get in there, and that will start to eat up your signal more than anything. But now for UHF and VHF, oh boy, I'd have to look that up. What you're looking for is the dB loss per 100 feet. And are you talking about getting up to like 432?
Yeah.
Yeah. So at
440.
432, it can become significant. Like for example, we had at school, we put in a satellite station. We had a 150-foot run from the roof down to the station, and we had a preamp at the roof. And basically, we figured we had upwards of 6 dB of loss coming down from the antenna through that cable. But the preamp helped that, and it was a low noise preamp. It was right at the antenna. It would switch in and out automatically on transmit, and it worked very well. But I don't know if you're not talking a super long run, are you talking about just something on the roof of your house?
Yeah, it's about 100-foot run altogether.
And well, that is significant. That could be, yeah, you want to watch your cable. So look at that decibels per 100 foot. That's the one you want to look at.
Would it be better to go with a direct burial cable?
Direct burial?
Yeah, so that it would have a thicker insulation, I would think, that
well,
would help with the UV.
It's not so much the insulation thickness, it's the insulation type. You want to look for something that's UV, it's called UV resistant. And the other thing that happens, by the way, thicker is better, especially at UHF. You get these small cables, they're almost like the size of a pencil thickness. They can be detrimental. Sometimes if you really, it depends on what you're doing. If you're doing like low noise satellite work, you want hardline or semi-rigid, things like that. But if you're just trying to hit repeaters, you probably get away with even using, I can't think of there's an LMR. We used LMR 4000 something.
400.
400, thank you, not 4000. Yeah, but that's hardline or semi-rigid. It's expensive, but it was a good thing, and it's still up there. So baking in the California sun.
Thank you.
Sir. Andreas.
Hello. So I have two questions about magnetic loop antennas.
Loop
So
antennas.
the theory, yeah, magnetic loop.
Yes.
So the theory, like being high from the ground, is that also true for a magnetic loop? Because I heard somewhere that you should put them quite low on the ground. That's the first question.
Yeah.
And the second is, I found that my magnetic loop antenna is very sensitive for how I run the cable. So if I run the cable in like just right down from the antenna, it behaves very differently than when I run it more around. Would you also recommend to put a balloon in that cable?
Okay, so I have to say I'm a little weak in magnetic loops. Are you talking about the it's a horizontal loop? It's a here, I'll draw it here. Is it something that's basically goes up and it has a circle like that, or is it a closed loop?
Yeah, it's basically like this, and there is a capacitor at the bottom.
Right here?
Yeah, and you have the second loop inside that.
I believe it is closed loop, and it is powered by the smaller loop inside that is just magnetically loaded.
Yes,
or connected.
like this. So, okay. I have to say I have limited experience with that. But if it's horizontal, the ones that I've seen before, they used to have something called a DDR. And that was an old concept, and that had to be operated over a very good ground screen. And it was essentially a piece of, in that case, it was open at the end, and it was driven by tapping into this. So this was grounded here, and then there was a tap along there. And this the whole thing had to be operated over a ground screen. And sometimes I think the height here was on the order of less than a meter. And they use very thick pipes, but that's my limited exposure there. I'm sorry.
Okay, no problem.
Okay.
Yeah, thanks.
But yeah, I'd have to look at the theory on that. I'd have to see what the mode of radiation is. And by the way, I take it this loop in the center, is this the same, roughly the same diameter, or is it a smaller?
It's the loop is smaller. It's
this one.
I don't know what the ratio is, but it's a lot smaller than the outer loop. Yeah.
So it's using this magnetic field to excite this outer loop.
Yeah.
Okay, interesting. I don't know. I can see the theory. It reminds me of that DDR, and yes, it has the old DDR system, like I said, had to be over a mesh ground screen.
Jay?
Yeah, and I think the magnetic loops should be.
Sorry, was there somebody with a suggestion there?
It was Buzz.
Yes.
I think what he's referring to is a small tabletop magnetic loop. It's got a capacitor to tune it. It's limited to the wattage of the capacitor for transmission, usually around 10, and highly directional, and they become very popular for inside apartments and whatnot. But it's like a three foot loop usually. Some maybe a little bigger, some a little smaller. I believe that's what he's referring to. And they're vertically oriented.
Okay. So unfortunately I have very little experience with that. I'd have to look into that. Might as well learn about it. So you said they're very popular. So it's called a magnetic loop antenna.
Yeah.
Okay.
Yeah, I don't think the height above the ground is particularly a big factor, but I'm not deep into the theory either. They really become, people build them, people buy them. They're quite popular.
Yeah, there's two ways. I do know that there's two ways that a loop can radiate. One is it would radiate in this direction, and then the other one is it can radiate horizontally, and it depends on the size of the loop.
These loops are a small fraction of a wavelength.
Oh, I'd have to see that one. I'll look into that. Okay, so Bruce.
So I have a question about coil shortened antennas versus non-coil shortened antennas.
Okay.
The efficiency of one versus the other. Maybe answer the question perhaps in the way of anecdotes. Like if you had two quarter wave radials, one coil short and the other not, and say that the radiation resistance for each was 49, and the insertion resistance was an ohm. So I get my question is, you mentioned that the efficiency of those two are different, even though the radiation power at the same currents would be the same. Is
Right.
it so? What causes the efficiency differences between those two? Is it? I mean, I know you said the length, but I mean, is it like a magnetic field density differences or something like that? Or
Well,
anyway.
yeah. So what's happening is you are essentially matching a lower impedance system with the coil. The coil causes the lower impedance system, which has actually a lower radiation resistance. Okay. And you're causing that to look like a higher one. And you're basically transforming your power. Now, the primary source of losses in those systems are the wire loss and then the Q of the coil. The Q of the coil could be is probably the biggest source of loss.
Oh, so then what you're talking about is the SWR bandwidth differences between the two.
Yes, one will be also sharper. Yes, one will be sharper because you're using the coil to tune things.
Okay, gotcha. So, sorry for the follow-up question, but okay, say assume you're operating both at the minimum SWR, and like I said, you had say the insertion loss was less than an ohm, and the radiation resistance was 49 ohms. Then in those conditions, would those two conditions have the same effectiveness?
So one is you got 49 and it's got an insertion loss of an ohm.
Both cases, 49 ohms, 1 ohm.
Well, no, because you can't have the other antenna can't have 49 ohms radiation resistance.
Why not?
Because it's shorter.
No, sorry.
You're talking about, okay, so there's a difference here. So for example, you're talking about the quarter wavelength radiator like this. That has approximately 49, or let's call it 50 ohms, right? That's the radiation resistance.
Right.
The antenna that you're proposing, and I'm going to pull the coil out of it for a second. Okay. This has a much lower radiation resistance. It might be on the order of 30 ohms. Okay. The coil, by placing it somewhere up on the antenna, makes it look like it transforms to 50 ohms. Okay. You see that?
Yes.
And you're trying to, but this radiation might be lower. It might be 25 to 30 ohms, depending on the height, how long the actual radiator is. And so your primary sources of loss would be in your ground, the wires, this wire, and then the big guy is this guy's Q.
Would
those by the way, what's that?
Yeah. Would those losses not show up on on an antenna analyzer?
No, if you're looking at it here, it looks like 50 ohms. And it doesn't show up as a loss, or I'm sorry, this thing, if this is it's a tuned system, it'll look like 50 ohms. You can't pick apart where your losses are. Now this, by the way, don't get me wrong, this one will not necessarily radiate. In other words, like let's say this is 25. Okay. So accordingly, if we were putting the same current into both antennas, we would say, okay, this one should radiate half the power as this one. But that's not the case here. Even though we're putting the same power from 50 ohms here, let's say we're shoving in here 10 watts in both cases. Okay. What happens is this 10 watts will turn into a particular current that goes into the antenna here. This one will be almost the same amount of current going into this antenna. I'm sorry, almost double the current going into here. Actually, no, I'm sorry, 1.414, in other words, square root of 2. So that the power radiated is almost the same, but you also have what's fighting you is this loss and the other losses, because compared to, see, this has a 50 ohm system. So if this has this wire here, let's say is a half an ohm, then the amount of current, power being lost in heating up the wire versus how much is going off into space is fairly low. In this case, the loss in the coil and the loss of the wire here in the ground can become more significant because this is so much smaller. You see what I'm saying? Okay.
Yeah. So when you're comparing efficiencies, what's the relative efficiency of one to another? Is it?
This one would be less efficient. I have not worked. I know I had one. Did I have one from the previous? Wait a minute. I did one in the previous lecture. Stand by. Thought I did one. Stand by. Okay. So in one case, so here we did one, which here's one. This is from my previous lecture. So we had here the radiation resistance in this one was very small, and it had basically, in this case, the radiation resistance was compared, so this was a 50 ohm radiator with 1.1 ohms. This was a quarter wavelength, and it was 1.1 ohms in the wire and the ground. And so basically you had this loss here, and the efficiency, if you did the math here, is very high. I mean, it's basically 50 divided by 51.1, which is, it's up in the 90s. Over here, and I hope is it still on the screen? You can see here, we worked it out, it was 7.7%. But this was a very low radiation resistance. This was like an extreme case where you had a coil that was on like this would have been much less than a quarter wavelength, like an auto mount or something, like a small antenna that you would use on a car. And we worked it out that the coil, look at what the coil resistance is. The loss in the coil was 36 ohms. Okay, and that's, by the way, this is a real measurement that was done. This is an example. I took this right out of the ARRL handbook. Okay. So this particular case, the coil inductance was 33 microhenries. Because of the Q of the coil, it had 36 ohms of loss. And therefore we got such terrible impedance. But this case, the antenna was significantly shorter with a radiation resistance of 3 ohms. That's an itty bitty antenna. You're way down. Okay.
So, and you're saying the feed point impedance of that is still the 50 ohms?
Yes. It's just dependent how that is being divided up. How that impedance, how much of it is radiation resistance, wire resistance, and then in this case, the coil resistance.
All right. Well, thank you very much.
Sure. Jack, you've been very patient. What's up? Is that a curtain array behind you?
It's a curtain array.
Okay.
It's a flare 9 antenna.
Oh, okay. Is it yours?
No. My question is, I've seen friends who've set up a 40-foot vertical antenna on the beach and run a single ground wire to a plate that they put out in the ocean.
Yes.
Are they fooling themselves, or are they actually getting a good ground?
They are getting a wonderful ground. Sailing, usually, by the way, if you're on the beach, there's a saltwater table below you.
Yes.
Okay. So you've got, if you're right down near the water, you probably are getting an excellent ground. That one's a beaut, because salt water is, what is it? It's well over, in some cases, 10 times more conductive than regular. Actually, it's maybe more than that. It might be several tens of times more conductive at RF.
So Now, and the other question I have
By the
is,
way, if I could just add one thing, that's typically done on sailboats. You have a copper plate. Even sometimes they put it inside the hull, otherwise it'll corrode.
done that, been there.
Okay.
The other question is, NVIS, can a vertical be used in NVIS, or does it have to be a dipole?
No. Yeah, it should be a dipole. Because NVI, yeah, because the whole point, a vertical has basically the pattern for a vertical. I'll just use another piece of paper. The pattern for a dipole, if you look at it, a dipole's pattern, if you're looking at it end on, it has basically, it's 360. If you looked at it from above, it's a figure 8, you know, like that. I'm truncating one side, but anyway, you get the idea. And so with the right height above the ground, you'll get quite a bit of radiation straight up. A vertical, on the other hand, the radiation pattern is more like this over a perfect ground, and over a non-perfect ground, it's actually more like this. So you get something. I'm sorry. Thank you. Thank you. So this would be a vertical. Notice here it has very little pattern going straight up, and even near vertical. I mean, this would be off. You know, this would be off at maybe about 20 or 30 degrees over a bad ground. So that's not nearly vertical enough.
Okay, thank you.
Sure. Nathan.
Yeah, thank you. So I was curious, so we're just talking about like total power emitted being a product of the amount of current and the length of the wire, but I know like
it's more than that. It has to do, yeah, there's a lot more than that, but it's okay. So it is, that's the next thing that plays into that. That's for a given shape of antenna.
Right.
The more current you have over a longer length. So if you have a dipole or a vertical, let's say, that's what radiates. What happens after that, though, is how let's say you had a long piece of wire or it was bent or something like that. It's how those fields combine at a distant point. Okay.
So I think, and maybe you're anticipating the next question. My question was like, so if you add more wire, you should have more like L to go into that. But I know you get to multiples of your wavelength and you start to get like extra lobes and weirdness. So like, is there a good rule of thumb for like trade-off between when you start actually having?
Well, you can use those. Are you familiar with a diamond?
No.
Okay. All right, a diamond array. Look up, by the way, if you want, there was a guy in the 1930s who used this. He was very famous out here in California, W6AM. And he used a diamond arrays. And you might find these, the ARRL handbook still has them in there. So what you have, and by the way, some broadcasters use this too, shortwave. What you have here is you can have this open-ended one, or you can have a terminating resistor. Typically, these are on the order of maybe several wavelengths, like 3 wavelengths. So they're fairly big, but they're set at a particular angle. And you anticipated this. You know that with a regular wire, as it gets longer and longer, you get these lobes that are like this. Right? I'm off the paper again, I know. Anyway, you get this sort of butterfly pattern like that. Well, in this case, they use those, they add up. So you can see what's happening on this wire. I've got a lobe that is going off this way. This wire is going to have one that is going like this way off of it. And the same thing is going to be happening here. I'm not drawing this necessarily very well, but we're going to try. And this one, so you see what'll happen is you can get these lobes all to add up. And they radiate very well. It's called a diamond array. And there's a terminated version and an open version. And you look in the ARRL antenna book, they still cover them.
Okay.
You just need lots of real estate.
Yeah, it's a big antenna.
Yeah. And it has to be a certain height. This, of course, is mounted. I'm going to try and draw it with a perspective here. You're on poles above ground. It was typically used for military work, and it has quite a bit of directivity. W6AM had his, they were all fixed, and they had them directed to Japan, the Far East, South Pacific, things like that. He operated off of the Palos Verdes Peninsula here in California, outside, it's near Los Angeles here. In fact, his antenna array was so effective that basically when World War II started, the military showed up and said, "Thank you very much for building our radio station." And they took it over.
Neat. Thank you very much. That's
certainly. Kuba, I think, has another question.
But if we have still time, because
how
we
are
are
we doing?
Excellent. Let's make a small case study. Small house with a very small garden. So the winter is coming. So top band
Give up right there. You've said it all. It's done. No, I'm kidding. Winter is coming. Oh my goodness.
Yeah.
Now we're gonna add drama here.
I've got 40 meters end fed, so it's good for 80 up. But I have nothing for 160. Practically, I can't touch the end fed to make it longer or anything, because once I get on the other house, they will politely ask me to remove what I have now. So I don't touch it. So basically, I can either try to throw another 40-meter wire. It's long, but as it will be mostly horizontal at 10 meters, I don't expect too much performance.
No.
I can't build 40 meters proper quarter wavelength vertical, but I can make 10 meters. I can make a loading coil at the center. Yes, it will have like 3 ohm or something like that. Yeah. So basically, is it worth getting into it, or there is another? What would you shoot for in this situation?
I would have to say, sounding like in your case, by the way, do you have radials?
Nope.
Yeah. And
I thought about elevated one.
Yeah, the elevated is okay. Depends on how you deal with your garden and whether or not your wife will let you do that.
I will do it over the metal fence, and I can stack there. I can't stack proper 20 meters. Oh no, 10 meter. 40 meters each side, but I could try to use coax, the PE coax that has 66% speed coefficient.
No.
It would
for what? You're
radio.
You're making your coils shorter.
No,
I meant radial shorter rather.
Yeah.
Yeah, that doesn't work, because what it'll do is, in this case,
I have like 10 to 15 meters each side of the antenna.
Yeah, but what I'm pointing out is the velocity factor does not figure into it.
Okay.
The velocity factor is only for the field that's going through the center of the coax.
Okay.
Anything on the outside, it's just like any other conductor.
Okay. So
but I would say the vertical with almost any, you're hamstrung there, no pun intended. But the thing to do would be a vertical, and you'll get out. You may not be the king of DX in 160, but you'll get out. I would say that would probably be your best bet, as opposed to a horizontal wire at 30. You said at 10 meters? Yeah, okay. Yeah. I'm thinking a vertical would be better, and any radials you can do, plus a ground stake. I take it you're in, if I remember, Poland is it's farmland, and so it's fairly good soil. It's, it's like medium conductivity, so it's probably okay.
Thank you very much.
Sure. All right, that looks like everybody that wanted to ask questions.
Thank you so much for being so patient and staying the extra time. That was fabulous.
That was, thank you. I was, by the way, I thought I'd do it again at 40 words a minute, CW. I don't know. Do you think?
Did you enjoy? I saw a couple smiles on your face during the CW that you attended before we came on here.
Yeah, it was fun. It was bringing back that, hearing the 0 degrees below zero. I mean, or sorry, yeah, below 0 degrees. I mean, it just took me right back to the copying the weather broadcasts and the same things. So yeah, it's fun.
Do you work much CW or?
Yes, but not nearly as much as I should. I typically am not much of a rag chewer on it, but I should get better.
All of us should.
Yeah.
All right. Well, thank you very much. And before we close out, I just want to make a plug for next week when Mark K6FG, who's lurking here, will be doing a similar presentation, but all about DXing. So I'll invite you all back. And thanks so much, Jay. Are you going to be there Thursday?
I'll have to check. I have to look at my schedule. Keep going, and I'll look at my schedule here.
All right. In any case, are there any questions about anything for anybody, et cetera, et cetera, et cetera? Okay, well then I'll let anybody and everybody who wants to go, go. Thank you, 7-3.
And I'll be there Thursday.
Well, that'll be great. Be nice to catch up and see you, and I don't know if we'll be able to see Gabe there. Probably not.
Well, let's hope.
Okay. Well, it's even once he's quote recovered, he may not be out and about for a little bit.
Yeah, right.
Maybe get going slowly.
By the way, I'm terribly impressed with how you've got people from all over the world. I see somebody here from Tenerife. Steve, nice to see you. And wow, that's quite an audience.
Yeah, it's I can't claim any part of it. I am handed students by the CW Academy, which is a worldwide CW learning school. So they sign up. It's it's a very American-centric school, but it's rapidly transforming into a worldwide school. The reason I get so many international students, unfortunately, is not because they like me or think I'm very good. It's because of the time I teach. I'm teaching in the morning here on the west coast of the US, and so I catch the Europeans during their afternoon and early evening, whereas most of the faculty are teaching in the evening in the U.S., and that's in the middle of the night around. I also have told the schools something. I don't know why others haven't, but I told them I will take anyone. They always have this thing about matching time zones, and I'm like, I don't care what time it is where the student is. They're willing to show up. I'll teach them. And so I get some bizarre stray. I've had people get up at 1:30 in the morning to take my classes in Western and Eastern Australia. And I've got a young woman who gets up very early in Hawaii. I don't know why. I don't know why she doesn't catch an evening class, but she drags out. That's Heather, who, by the way, said to say hello and apologize. She had another commitment that she couldn't make. This.
Well, I'm glad we got her problem solved, pretty much.
She seems very happy, and she's now working CWT from her apartment and gathering contacts, whereas I think she had 0 before, so yeah, she's happy. Was I correct in that she's making the whole radio station behave? That she complaining to them? Did she complain to them and make
No,
them?
no, it's not their fault. The thing is that she put in a filter. The reason it's entirely her receiver. It's because the local oscillator, I looked up the schematic on that receiver. The local oscillator is basically feeding square waves to each of it's an SDR receiver. So it's basically a 0 frequency IF. So basically the local oscillator is at the same frequency that you're receiving.
Okay.
And it's feeding square waves into there. And even if you filter those, you're going to get enough harmonics. And so what was she at? She was like the 7th harmonic or something of the station was at that frequency. And it's an odd harmonic, and it was just blasting through all the front end filters. It was so close. I mean, you got, tens of kilowatts, if not more, splashing in there, and it actually will get in through her power supply. It's that bad. And because she's still got residual, and but it's a lot less. And it was the whole problem. Her front end was just not, it was being totally overwhelmed. It didn't have the really, it needed an extra dose of filtering.
Is this a 7300 you're talking about?
No, I thought she had a K something. Was it? I'd have to look at my emails, but I've forgotten now, but I did look it up and see that it was exactly that. I know that chip that they're using. It's a lovely chip. It's basically a clock generator.
It's a it's a QRP radio.
Yes.
Right?
Yeah.
What's
I don't
an
remember what the
SDR QRP radio?
Yeah.
Is it the ICOM 705? No.
No, I'd have to look up my email. Stand by. Let me see. Hold on.
What, a K2 maybe?
I thought it was a K2.
That's not an SDR radio though.
Yeah.
What about putting a notch before the front end at the antenna?
Well, what she did was she put a okay, hang on a second. It is blah blah blah. It's a KX2.
Okay.
And she got an MFJ 702B low pass filter, and that's what did it.
Great.
So, but I mean, she's basically looking at, yeah. Right. So she was, yeah. So anyway, it looks like it did the trick for her.
Why a low pass filter?
Because in her case, it's the transmitted harmonic. The transmitter is getting in. So she was at 98.5, was getting in there, FM. That was coming in the antenna, getting into her front end. And
I thought it was the other direction. I thought it was AM broadcasts and harmonic.
No.
Cool.
No.
Well, I'm not sure how many people would have been able to solve that for her. She's very, very, very happy and making contacts all over the place now. She used to have to pack up and leave her apartment to get on the air. And,
yes. Who is she?
She's on Oahu, isn't she?
She's on in Hawaii somewhere.
Yeah.
Very close.
She has this FM station that is like, I think she said it's less than a mile. And she's up on a hillside, and the other antenna is, I don't know, on the same or another hillside, but basically it's just, slamming into her.
Right. Did you want to know her call sign?
No, that's okay. I thought maybe it was one of the locals here.
Well, local when there's atmospheric ducting from Hawaii, you can get on with her. No, she's in Hawaii. She's the fascinating person. She's an astrophysicist who co-wrote, I guess, I'm guessing, but maintains also the database for all astrophysical objects in the universe. It's a, believe it or not, SQL database of billions of objects. Every known object in the universe is in this database. And she is the sole person that gets up in the morning and takes care of it and maintains it.
I'll bet she's busy now with Jack Webb.
She told me that she put some kind of governor on it because no search should last. I think it was like 2 or 3 days.
Yeah.
For a search to last.
Yeah.
You usually come back with how many microseconds a search lasted. She's capped it at 2 or 3 days for a search.
Wow. Yeah.
So that's a big job. Big job.
I've got a question, guys. I'm getting my monitor. I'm getting a message across my monitor that my internet connection is unstable, and I don't know if that's coming from my end or from your end. It's your end.
It's either your internet. It's not here, but it's either the your internet connection or it's the server between.
Yeah.
But we're all fine. Everyone's fine. Raise your hand. Yeah, you're freezing, Mark, but no one else.
Yeah, and you were also flanging there for a little bit. Yeah, I think it's on your end, Mark.
He's frozen now. If you turn off your video, Mark, then you'd bring back your audio.
Wow, that's pretty bad.
I don't think I can. Yeah, that's totally bad. I've not seen him like that before.
There he goes.
Thank you. It's still a problem. Is it?
Yeah. Talk to us. Let's see if
It's still a problem. I can see. Maybe I'll just reboot everything.
All
okay.
Right.
Hello. 1, 2, 3, 4, 5.
We hear your audio now. That's better because the video is something like 90% of the.
I can tell that it was delaying. Before what I'm going to do, I'm just going to reboot everything. And guys, I'm going to go and I'll be.
Yeah. See you next time.
All right. See you tomorrow.
Yeah.
Seeing you, Buzz. Okay.
I'm going to be sitting here watching him trim my trees.
Trim your trees. All right. Well, what I do is every time I have the tree trimmer come, I have another wire antenna put up in the top of the tree. I'm like, woo, trim the trees. Yeah.
Yeah.
By the way, could you just take this up to the top?
Don't worry. It's not energized.
Yeah.
I did that once in my first house. I had him climb a palm tree and he's looking at me like I'm holding it. And I said, look, it's fine. I'm holding it, And I actually at one point I stuck the end of it in my mouth to show that it was not live.
It's a fact. 2 out of 3 homeowners will electrocute the tree trimmer.
Well, that warning about guys putting up antennas near power lines, I cannot tell you how many times I read that in QST.
Yeah.
WXYZ 42 was killed the other day. He had a vertical. He was holding up the vertical. The wind got it. It fell into the power lines, and he was still holding it.
I was charged with designing and building the ham radios communications, all the communications at the local disaster operations center. It's just it's a double wide for our town. And so I'm putting all the antenna farm up at the roof. There's quite a lot of radio stuff going on. And they were complaining, why you're smushing it all together at one end of this thing. And I said that's because the tallest antenna cannot fall and hit the power feed coming in on the far corner of the building.
Right.
And they're like, no, it's fine. It's fine. No, it's not fine. It's not fine. It's not to mention that it's a disaster operations center. It's supposed to go operate in an earthquake. Well, what happens in earthquakes?
I think power lines have been known to fall down in earthquakes.
I just, 10 years later, long after I was done with it, they finally buried the power line. They went to move it again. I hear the gossip. They went to move it, and not the power line, the antennas. They went to spread the antennas out. I think they actually did. ignoring the safety stuff, and then somehow somebody like really leaned on them, and then they finally buried the power line underground to come in.
Yeah.
And they lived happily ever after.
Yeah.
But, yeah, I try and tell like all my classes the same thing.
Yeah.
Not only can the power lines not fall on your antennas or the antennas fall on the power lines, they can't fall on each other if they all come down.
Right.
It's a simple, hard stop.
Yeah.
You just can't do that. You go find another hobby before you do that.
Right, because they're basically unfused on that, you know, the feed side. The fuses are all at the antenna head, or not the goose head.
Once they hit, they're fused.
Yeah. Completely and utterly fused.
Anybody have any questions, or just hanging out and having fun while his trees get trimmed? Just take a little off the top.
Yeah. No, I've got some major, and I've got to take down some antenna ropes today. I've got my inverted V is tied off at the ends of the property, and it's basically a pine fern hedge that goes around the back end, and so I've got to pull all those down and get them out of the way.
Yeah, in the high fire danger areas, we have another name for that. We just call them Roman candles.
Well, you know, it's funny in this case, pine ferns are the one thing that have thrived. I don't know if they've got roots that have gone down to where the water table is gone, but man. Yeah, see you later, fine. Kuba. Nice meeting you.
Bye, Kuba. Take care.
Thank you very much. See you.
Yeah, they'll find the water, but they're full of pitch. They're just nothing but pitch sacks, and you touch a match to them, and
you're talking about pines or pine ferns?
Pines.
Oh, these are pine ferns, but okay.
Ferns. I'm not
pine
familiar
ferns.
With pine ferns.
Yeah,
I'm assuming they were some sort of pine tree.
No, actually, the only reason they're called a pine fern is they have they're somewhat aromatic and they smell a little bit like pines, but they have more. The leaves are more. They're thin blades, leaves, and they're great. They grow like crazy, and even though, you know, out here in the valley, they do real well, and I have to have them trimmed every 2 years.
I have all these protected oaks all over my land.
Oh, wow.
I'm not allowed to touch.
Yeah.
But they're coming down. The drought is killing them.
Yeah.
I'm having 100-year-old trees come down.
Oh, wow.
Tree guy tells me, he brings down a branch and shows it to me. It's all charred from the very top of the tree. He's saying, you know, fire came through here when these trees were very young.
Wow.
And, I know the fire came through before 1927.
Wow.
So he's showing me a branch that's still charred from before probably just before 1927.
Wow.
But yeah, there was a fire in Calabasas yesterday along the 101 in Calabasas, not too far from you. They put it out at 10 acres, I think.
Well, we've had 2 up here at the end of the street.
Were they hard to get going?
Sorry again?
Were they hard to get going?
No. But it seems
don't want to walk too far.
No, but man, I mean, it was it was like Vietnam here. The helicopters just one after the other, and they were using a fire hydrant at the end of my street here as the fill station for the ground attack.
Yeah.
And the trucks would come down, they'd come back down DeSoto, fill up, do a U-turn, go back up. But what was dumb was the police didn't close DeSoto because the trucks were having difficulty turning around because there was still traffic. You know.
So down in DeSoto, down in Northridge?
I'm actually at DeSoto and Rinaldi, so I'm right up at the end of it. Okay. Just before you hit the 118, and the fire was just at the 118 in DeSoto.
I remember those, yeah.
Yeah, there was 2 of them.
Yeah.
One right after the other.
Yeah.
So. Yeah, well, I'm hoping that that will be it. Although we're supposed to be warm this week, it's supposed to get cool again.
Another heat wave.
Yeah, well, not so bad.
97 today here.
Yeah, it's not too bad.
Not like the 113s. Yeah.
No.
Yeah. Anyway, anyone have any ham questions? No? This is your big chance. No,
Yeah.
we're just talking local trash, you know. Have you burned up yet?
Doing all the stuff we were going to talk about tomorrow.
Yeah, go ahead, Steve.
Yeah, okay. One quick question I could have asked earlier, but I'm going to take your idea away of maybe putting a plate for a vertical by the sea, because I can do that probably the next couple of days for the radials. That sounds quite a good idea to actually put it in the water. If I've got an end-fed half wave here for 40 meters, 20, and with a capacitor for 15. I've also got a dipole for 20 meters. Theoretically, would a dipole for 20 meters be better than the 40, which is at 20 meters as a full wave? Or are they in practice?
Well, you're going to change your feed point, and I take it you've got a tuner at the radio. And how long?
They're both with a balun. So the dipole hasn't got a balun in it, but I've taken that idea. It's only 5 watts. It's QRP.
Yeah.
The end-fed half wave has got a balun. It's got a transformer in it, so that comes down to a good estimate. So SWR, both of them is good, but theoretically, if you've got 20 meters of wire, given a full wave at 20 meters, if you want to use that for a full wave at 20 meters, is that better theoretically than a half wave dipole? Or
can I ask a question, Steve? Are they at the same height? Because I think
same height. So we've got 7 meter on a 7 meter pole, and they're both off the ground. So they kind of mirror each other in thing. They're not less than 90 degrees there. Yeah. And they're running down on long sort of tie lines, if you like. So they're both off the ground.
Right.
Any thoughts theoretically? What would be better?
So you said
the end-fed half wave is easier.
How long is the run to the shack from the dipole?
Well, it's not a shack. This is portable. So literally from there, it's like a 7 meter. So it's probably like an 8 meter run.
Oh, just down to your station is right below it. Got it.
Sitting beside it on the beach, or not on the beach, or just wherever.
Yeah, and I take it you got a tuner that will take care of it, and because you're going to get some loss. I mean, the impedance of the full wave dipole will be. Hang on a second. Oh, you're going to be at a half for both of those. So you're 20 meters on a 40. So your feed impedance is going to be fairly high. And you say there is a balun there or isn't?
There is on the end-fed half wave. Yes, it is a balun. I mean, they both come down SWR 1.0, 1.1.
Yeah, I'm talking about the dipole. Dipole is no balun?
There's no balun, no. Not at the moment, not this one, no.
Yeah, because what you're going to end up with is, and you said 7 meters, so that's like, I'm just doing some quick math in my head, what that might transform into. You're going to have, your tuner may have to work a bit to get that right. You're going to lose something in the tuner, and you're not going to lose a whole lot. The cable's too short. I mean, meaning it's too, it's not long enough to really contribute a lot to loss. I'm just wondering if your tuner, have you tried seeing if your tuner will reach and tune it?
MTR3B, so which is no tuner in it, so I can.
I'm sorry,
tuning up.
I got only part of that. I'm sorry, for some reason.
Okay, so I can tune it up with I can use an MTR3B, which is a small QRP tuner.
Yeah.
A small QRP transceiver with no tuner in it.
Right.
So it will. I can check the SWR. So the SWR set looks good on both of them.
Okay.
But it's just really you've got half a wave 20,
right,
or a full wave. Is there any?
Yeah, there would be an advantage to it, provided that you can get a decent match. And like in your case, the cable is not terribly long, and you might get some RF from it. So very well. Because you're feeding those with a 20-meter dipole, you're feeding those at the high voltage point. And so you're going to get quite a bit of, you could get quite a bit of action on the coax with RF coming back down. So yeah, I think you could do that. And I think the dipole would work, the 40 dipole would work better. You can try it. I mean, what it's going to do is it's going to distort your pattern. So I've got to look at the patterns. It was like I was showing before, the gentleman who asked about the diamond antennas. As you get, depending on the length, your pattern's going to change. I have to look at that. Stand by one. I'll be right back. I'll look at that.
He's going to run out in the backyard and build one.
No, this is literally, Buzz. I've got, so it's just a theoretical question. Half a dipole for 20 meters, so you've literally got a half wave, or using an end-fed, which is for 40 and 20, which is a full wave on 20 or a half wave on 40. The SWRs are the same.
My thing with a halfway, with the end-fed, I'm not a big fan of them. Usually you need a tuning stub on one. And also, what ends are you putting up? How high, and what are you doing to keep? Are you using the coax as part of the antenna or not? And if so, where is that? Well, you're using very short coax.
That's right. Yeah, literally, it is. Yeah, it's just short. I mean, on the end-fed half wave, it's probably coming just under a meter off the ground at the lowest point. I suppose it comes down to.
Yeah.
So it is coming down.
I mean, if you can get a dipole, if you want to do 20 meters, if somehow you can pump the dipole up to 33 feet at the center, that's the radiating portion of the dipole.
Yeah.
And the rest is more to balance it. Obviously, it radiates some as well. But if you can push that dipole up to 33 and then get the ends, somewhat off the ground on 20 meters, that's the winning formula by far.
Yeah, because where I am here, it's mostly 20 meters and up, and sort of 17, 15, because in the daytime when I'm going out 40 meters, you're not going to hit other land really,
Yeah, so they now have these, these very portable, collapsible, pull fiberglass or carbon fiber pulls, so you can get one up. If you're just putting a little wire up, you can probably get one up 33 feet, and put the middle of your dipole there, and then do whatever to get the ends up somewhere off the ground. And I would think that would be the winning thing. I would just try to get a 20-meter dipole up.
Yeah, that's what I've been using that. So I've got both of them here, but I was just wondering, the theory wise, is one better than the other? Because one's got more wire up. They're both kind of showing resonance, but it's really, I suppose the 20 meter, that dipole is higher. So it's probably most of it's higher.
You got the right guy to answer your theoretical question. I'm more practical.
So it turns out that the two-element collinear. So basically what you're forming is a two-element collinear array. And what it does is it makes the figure 8 that you normally get from a dipole much slimmer. In other words, you've got more directivity perpendicular to the axis of the antenna.
Right, okay.
And that's that. Right. So you're getting that. So the whole question becomes matching then. And it sounds like you're not doing anything that's going to kill you on matching.
Oh no, it's only Right, that sounds great, Joe. Yeah. I mean, I've got a vertical as well. So the vertical by the sea. I mean, literally on 5 watts. This is over Christmas time. I was hitting Fiji. We're on the RPN network. Wow. Fiji is about 18,000 kilometers away.
Yeah.
Which is about 13. and that's on 5 watts. I got an RBM report back. Couldn't believe that, you know.
Yeah. Yeah.
But you'd literally just the Atlantic there, it's going over that way, and that was in the evening, so that was on the grey line.
Yeah, and you got a great takeoff, and
Yeah. So
So
I'll try the putting a plate in the water as well. I'll take a little plate out of my backpack and drop that in on the end of the
yeah.
radial. And see
How big a plate are you thinking?
Something lightweight that goes into a
Yeah.
into a backpack. So it's got to be lightweight.
And by the way, it does not have to be a solid plate. It can be a screen. You can do something with, and I suppose the biggest question is corrosion. So you know, eventually you got to clean it and keep it from corroding, but it does not have.
He's taking this home every day, right?
Yeah.
Oh yeah, this is right. It's just I was thinking maybe like a piece of aluminium plate just that goes in your rucksack. I don't know if aluminium will be a good conductor like that.
It would be okay. It's just a question of, I mean, it's all right from what you just showed me. I mean, you're talking about something that's the size of a large book, maybe.
Exactly. Yeah.
I'd say get a piece of screen, like a mosquito screen or copper screen, and roll it up.
There's a thought.
That's
very lightweight screen.
Yeah.
Yeah.
But wash it. You have to wash it every day.
I can do that. Yeah.
Yeah. But I'm almost wondering if, you know, with the way you are, if the plate is really going to buy you anything. I mean, the other gentleman, I was thinking something that was more like on the order of like maybe about 2 meters square or something like that, much larger, which is what you would put on the bottom of a sailboat.
Yeah. So in the UK, I mean, in the UK, I live on a narrowboat in the UK, which is like 60-foot steel bottom. So if I use the vertical on there, that's pretty good. You get a good ground there. But you've got solar panels and all the rubbish you get with switching stuff like that.
Yeah.
Makes a noise, isn't it?
Right.
Anyway, Joe, well, thanks very much for the talk.
Certainly.
That's great. It's nice and practical, which is a couple of ideas to go away with, which is the whole idea.
Good.
So.
And
right, I'll leave you guys
hear how they do. Sorry.
Okay. And thanks very much. I'll let you guys to finish off your chat, and I'll catch you again in the week, Buzz. Yeah.
Great. 7-3.
Thanks very much. Appreciate that.
Have a good day.
Okay. Bye now.
Okay. So Buzz,
recording.
Yes, for 2 hours and 15 minutes, but